Welcome you all to the Random Vibration Analysis webinar, which is given by midas NFX platform. Thank you very much for being with us. I'm Eric Braverman, CAD/CAM Israel CEO and Application Engineer. If you have any question during this presentation, please write it in front of you and please raise them in the end of this presentation by the QA section. I will do my best effort in order to answer all these questions in the end of this session. The duration of this webinar is 1 hour and I will allocate 10 minutes for question. So let's go through the agenda. We will speak about what is random analysis. We will differ between deterministic analysis and random analysis in the point of view of vibration. We will differ between sine vibration and random vibration. Let's do a little discussion about the PSD curve, which is the load for the random vibration. Time frequency domain by Fourier series and Fourier transform, and vibration mix mode, of course. We will discuss about the fatigue minor, which is one of the outcome of random vibration, about the rule commutative damage model. Random response analysis process. In order to do an analysis, random analysis example also will be given during this webinar. We will show and present the results and of course allocate some time for Q&A. So what is random analysis? Random vibration test is one of the comprise of vibration energy for all the frequency over specified range. The random frequency component that make up the input signal for random test combine in the amplitude phase to create time waveform. The waveform appear on the oscilloscope as random noise while we measure it. So random is a combination and consolidation, of course, of many and maybe infinite sine wave. Let's discuss about deterministic vibration and random vibration. So deterministic vibration is one that can characterize precisely, whereas random vibration is statistically analyzed. In mechanical system, deterministic vibration are excitation that excite response from the system. So let's concentrate in the bottom right of this slide. We can see 3 examples, also in the time domain as well as in the frequency domain. In the frequency domain, we can observe 3 peaks on each curve. Those are the natural frequency of the system, whereas the sine vibration have very accurate and precisely determination from the amplitude, from the phase, and from the frequency. Sine vibration versus random vibration, the major difference between them, between the sinusoidal and the random, lay in the fact that for a later, numerous frequency may be excited in the same time. So many frequency we can see at the same time, whereas in the sine vibration, we can see them separately and not in the same time. What is PSD curve? PSD curve is the load curve that we load the system for a random vibration analysis response. The PSD stands for power spectral density of the signal. The PSD present distribution of the signal over the spectrum of frequency, exactly like the rainbow that present distribution of light over spectrum wavelengths. So Here we have an example of a random load that we load the system by it. In the vertical axis, we have the ASD or the PSD in the unit of G square per hertz, and the horizontal axis is the spectrum. The spectrum, which means the frequencies that we load the system. Here in this example is between 10 hertz to 10,000 hertz. What is the power? The power is the integral under this graph. After we make the transform by transform Fourier from the time domain to the frequency domain. Here is the peak, the first frequency, the second, the third, the fourth, and so on. So the integral under this graph is the value of G square. Here in this example is 0.0053 G square. And the root mean square of this value is 0.73 G, which is the power. The mean square value, we will try to understand it via those following example. Here we have two wave sign, the red one and the blue one. They have the same amplitude, however, they have different frequency. When we combine, when we add those two signs, we get the following curve. Part of it is under zero, part of it is zero, and part of it is about the zero, because we combine it as it is. Here we have A square, B square, which have the same amplitude, but another frequency and the same phase, and we combine them and add root mean square, which is 0.5. And here we combine A plus B square and have the mean square on 1. Here we can see that all the value in this example are above 0, because this is square and also this is square. So it's very important in the evaluation of the PSD. Why spectral? The frequency distribution of signal is very useful information when dealing with system having resonance. The peak in the frequency spectrum of the tip vibration clearly show the resonance frequency. First, second, as I show it before. Time frequency domain, Fourier series. Let's see the 4 examples of waveform that have another different amplitude, different phase, and different frequency. And let's see the time domain, the frequency domain, and the amplitude. Let's try to understand it via those two films that I will radiate it right now.
We have an x-axis and a y-axis. Let us also create an axis that represents the angle theta. The green line rotates by the angle theta. For each value of theta, the x-coordinate represents the cosine of theta, and the y-coordinate represents the sine of theta. The angle theta can range anywhere between negative infinity and positive infinity. This two-dimensional pattern is what we refer to as a sine wave. We can change the sine wave's amplitude, phase, and frequency. Suppose we have two sine waves that are identical except for the fact that they have different amplitudes. If we add these two sine waves together, the result can be represented graphically as shown. Now, suppose that the two sine waves also have different phases. The sum of these two waveforms can be represented graphically like this. So long as the two sine waves have the same frequency, their sum will always be another sine wave of the exact same frequency, but with a different amplitude and phase. Now, suppose that the two sine waves also have a different frequency. If we add together sine waves of different frequencies, then the resultant waveform is no longer a sine wave. We can add together three sine waves. We can add together four sine waves. We can add together five sine waves. In fact, we can add together an infinite number of sine waves. Here, by adding together an infinite number of sine waves, we have produced a pattern that looks like this. Now, let's add together a different set of sine waves. By adding an infinite number of sine waves, we have produced this other pattern that looks like this. As it turns out, every possible waveform and function in existence can be generated by just adding together different sets of sine waves. In the two examples shown here, the sum of all the sine waves happened to be repeating waveforms. In these cases, only certain frequencies of sine waves were needed. And each of these sine waves had a measurable amplitude. Non-repeating waveforms can also be generated by adding sine waves together. But in these cases, sine waves of every possible frequency may be needed. And each of these sine waves have an amplitude that is infinitely small. When an infinite number of sine waves with infinitely small amplitudes are added together, the result can be a waveform that we can see and measure. This is the same way in which, if we add together an infinite number of infinitely thin sheets of paper, although each sheet of paper by itself has zero volume, Their combination can be an object with an actual volume that we can see and measure. Some sheets of paper can be larger than others. Although the volume of each sheet of paper by itself is 0, when we have an infinite number of sheets of paper added together, we will be able to measure the object's density, and the density in some parts of the object will be higher than the density in other parts of the object. Similarly, when we add together an infinite number of sine waves of infinitely small amplitudes, we will be able to measure the density of frequencies. And this density of frequencies will be higher around some frequencies than others. This is what we refer to as the frequency spectrum of a waveform. All signals and waveforms have a frequency spectrum. When signals and waveforms interact with physical objects, their frequency spectrum is altered. By understanding how the frequency spectrums are altered, we can understand how the signals and waveforms are altered. The signals and waveforms that we see in real life have a beginning and an end. However, each of these signals and waveforms can be thought of as the combination of an infinite number of sine waves, and each sine wave has no beginning or ending. It is just that all these sine waves exactly cancel each other out at all times, except during the time that the signal is present. Therefore, all signals that we see in real life can be thought of as the combination of an infinite number of sine waves that have always been present since the beginning of time, and which will continue to exist through all eternity.
So I do hope that you enjoy from the film that give you an elaboration about the transform Fourier series and how we implement them into the random vibration application in our field. Right now, I want to screen you additional movie that will give you a deeply understanding regarding the time frequency domain Fourier series, which is FFT, fast Fourier series in our application and measurement.
The fast Fourier transform, or FFT for short, is an algorithm used in data analysis and signal processing to break down a vibration or signal into its individual frequencies. To explain this further, we will listen and look at a recording of the musical note A. The waveform tells us the amplitude of the vibration over time. Using the fast Fourier transform, we can translate this waveform into a frequency spectrum to decipher the exact frequency that exists in this recording. The frequency spectrum measures amplitude over a spectrum of frequencies rather than time. We can see that this frequency is holding at about 440 Hz, which, if we're still talking about music, is an A note. If this A note showed up oscillating at a frequency of 400 Hz instead of 440 Hz, we would know that the musical instrument is out of tune and needs to be fixed. Now, you wouldn't use the fast Fourier transform to tune an instrument, but this example is similar to the method used when monitoring machinery vibration. By dissecting signals into their individual frequencies, we can determine if any parts of the machine are malfunctioning.
So let's speak about the PSD curve type, which called vibration mix mode. There are 3 mix mode vibration testing. And they are sign on random, SOR, random on random, ROR, and sign on random, SOROR. Let's concentrate on the bottom left side of this slide. It is PSD curve for helicopter, and it's comprised from the PSD continuous curve and a 3 wave sign, 1, 2, 3, 4. Those are the sign on the random. And let's see this PSD curve, which comprised from the continuous PSD curve and 3 narrow bandwidths. This is for track. This presents the track vibration condition that the track should be exposed to. The 2 standards that illustrate the testing method, standard for environmental engineering condition, vibration of course condition in the laboratory, are elaborated in MIL standard 810 and DO 160, which is environmental condition and test procedure for airborne equipment. What is GRMS? We have already spoke about, but let's drill down for this issue. GRMS, sometimes written GRMS, or in capital letter or in small letter GRMS, is used to define overall energy or acceleration level in the random vibration. GRMS, root mean square, is calculated by taking square root of the area under the PSD curve. So it's not, we have to do the integral or the sigma, and then to get the root mean square under the curve. So here is a very simple example which elaborate the frequency range overall, and the ASD or PSD, which define in G square per hertz, and in part of the curve, the slope of the curve in unit of dB per octava. And at a total, the GRMS is 6.8 GRMS. The Gaussian and the sigma clipping, Gaussian distribution. So let's elaborate what are the following percentage. 68.2 define plus minus sigma, which is the lowest time that the system exposed to, plus minus 2 sigma, which is 95.4% from the time, and 99.7 define the the 3 sigma time the system exposed to. This is the Gaussian distribution, and this is the elaboration of the percentage for 1 sigma, 2 sigma, and 3 sigma. In order to calculate the GRMS, we have to take into account several parameters as will be defined in this slide. The slope here in the portion under this curve that paint by color red is dB over octaves, and the dB is 10 log ASDH over ASDL. This is ASDH, this is ASDL, and the octave is log FH over FL divided by log 2. Then we have all the parameters in order to calculate the slope of the curve in this area, and then we can calculate the area under the curve, and then we can make the root mean square in order to calculate the GRMS. And of course, we can calculate all the other area under this curve in order to have the total GRMS. A cumulative damage model, which defined in fatigue minor rule. I have to elaborate and to tell you that midas have a very spatial model in order to analyze fatigue, and this is due to the random simulation results. We can analyze in midas the fatigue by minor model and many other model which are elaborated in midas. So the calculation of minor based on sigma I equal 1 to k ni, which is small ni, over big Ni, and this is equal to a constant. And this constant is the fraction of life consumed by exposure to a cycle at different stresses level. In general, when damage function is reached to 1, the system is in a failure mode. So this is the SN curve. The SN curve present in the vertical axis is stress. The horizontal axis is the number of cycle, and this is actually a logarithmic curve. And of course, the minor rule can be calculated in several ways. Wi equal to small ni multiplied by Si, and Si is according to number of cycle ni. And the W failure is equal to a big Ni multiplied by Si, and then we have the opportunity to achieve the fraction of life, C. Okay, what is the procedure in order to do a random analysis? So the procedure is to have the geometry and to import the geometry to midas software, then to do the finite element meshing, and then to define the material attribute set, to define the boundary condition, if it fixed, or other boundary condition, and also the external load on the system. Modeling additional mass, which can be concentrated mass or other mass, with the inertia around X, around Y, around Z, and then to apply the system to the load, which is PSD curve input, and the input load evaluated by frequency and PSD input data. Of course, we should define the analysis case, which is random analysis. The option to set is to define the damping of the system. Actually, if it's assembly, it's 5%. If it's signal part, it's 2%. And we can define the damping as a function of frequency also. Direct structure damping input, damping coefficient can be applied double of damping ratio. Dominant frequency we can also define and apply the lowest natural frequency. We define the random response analysis in midas, and then we get the results and study them. We can get the RMS response check from the point of view of stress and deflection, and we can get the response of PSD in each point of the system. Let's jump to a very elaborated but simple example that have been done in midas software in order to get the results by random analysis in an optical system, which is very important because the optical system have a displacement and stresses that sometimes cause a damage to the system, and it's not work functionally okay if the load is over the load that the system can be comply with. So we import the geometry as I illustrate before. By the way, then I will show you how to do that in midas software. But now let's concentrate in the slide. So import, and then we have the opportunity to import the CAD file by XT, by step, by SAT, by any general format that we want. Also, we have the opportunity to import by the Pro-E model, the CATIA, the Solid H, SolidWorks, Inventor, and so on. So the import of the geometry include the import of the external shape, as well as the import of all the internal part which include inside the system. After import the geometry, we have to do some activities in order to simplify the model and in order to achieve very high quality mesh. In order to do that, the outcome will be a very simple model by removing hole, removing fillet, merge surface, removal face, small faces and line. This will be given the opportunity to give us very high quality of meshes. Let's see that afterward in the meshing paragraph. In the meshing paragraph, we not only define the hybrid mesh, for example, which include hexahedral, tetrahedral, and pyramid elements. We define also the material of the part that we mesh, and all the part, the material of all the part will be defined during this stage. Of course, all the internal component, optical component will be meshed as well, and the final mesh was used in order to find the element in the internal parts, especially optical parts. And also we test the mesh by the following pass and fail criteria parameters like aspect ratio, skew angle, wrap, taper, Jacobian ratio, twist angle, and element length in order to be sure that all the pass criteria are valid and give us very high quality mesh. So we also have an outcome of the distribution of element type like tetrahedron, 40%, pyramid, 46%, pentahedron, 3.6%, and hexahedron, 10%. So in total, we have about 150,000 elements in this project. Of course, we define the material, we define also the property, and then we jump to the boundary condition, which define the boundary of the mounting faces of the model in order to fix it to the external world. Then we define the PSD curve in order to define the load, and this is by frequency column and PSD column as present in this slide. Of course, we define also the frequency load, which will be in the x direction, will be multiplied by 1, and the 1 refer to the PSD curve. And then we define the modal damping function, and we have 3 alternatives. One of them is constant, as we use in these analysis, 5% of damping, frequency dependent, and mode number. Those 3 alternatives can be taken into account, of course, one of them. If we use isolator, for example, we should take into account the damping coefficient, and we should calculate the damping, the critical damping, according to this formula. The calculation of zeta, which is the damping factor, is C over C critical, and the transmissibility is 1 over 2 Xi, while Xi is C over C critical. If we have, for example, a system with 1 degree of freedom, the resonance, the natural frequency can be defined by 1 over 2 pi multiplied by square root of k multiplied by g over w. We should strive to be in this area because this area is the region of isolation, and 2 numbers should be taken into account. One of them is f desired over fn, over the natural frequency of the system, should be square root of 2, and this is the border between the amplification and the isolation. And 1, of course, is the maximum transmissibility, while the fd over fn equal to 1, and this is the resonance. We should define the analysis case. First, we should check the frequency. So we run modal analysis. So this is modal analysis, and we get the results. I will elaborate them while I present it in midas, NFX. And then we do a random response analysis by defining the case of random response. We define the frequency increment, 50 in this case, frequency increment, which is 60 cycle per second, which is 60 hertz. Every 60 hertz we will have calculation. Number of increment will be 40. So the span is 2000 hertz, between 10 and 2000 hertz. And of course, we define the power spectrum curve, frequency load X, and the frequency function, which is the PSD curve. Also, we can define if we want the results on 1 sigma, 2 sigma, and 3 sigma, which are the time function that the system exposed to, and also to run the system and to get the results. We can get the results also on the graph of of G, which is the vertical axis, and the spectral Fn, 0 to the maximum span that have been checked. Also, we can present the stress as a function of frequency, while this is the stress. This is the minimal stress in a node of the system that suffer the minimum stress, and this is the maximal stress function of frequency. Let's then we can present the G by mapping, and then we can present the displacement mapping and the stress mapping. And also, before I go to the Q&A, I want to present you the midas software and how we work on it in order to build the model and get the result. Okay, the geometry and the simulation models have been prepared before in order to save some time, so that I will show you the preparation outcome. Let's go through the midas NFX software in order and procedure in order to show you the hands-on. But before, I will survey the midas NFX screen platform in order to let you be familiar with the main feature. So, it's very user-friendly to use midas NFX because you only have to go through the vertical menu first. So, the vertical menu have the material, the properties, the geometry, the mesh, and the connection between the parts. So it's very, very user-friendly. The horizontal menu, in the horizontal menu, we have the model, which include all what I mentioned before, the meshing, the properties, the material, and the connection between the part. The LBC is the load boundary condition. So we have the opportunity to insert all the boundary condition, the connection to the external world, and the load. In our case, the PSD load. And the analysis case, we have to choose the analysis case, either it modal or it random response, and run and to get the result. So that's all. So the first activity is to load the geometry. So we have to import the geometry. It is very simple because we have a lot of platform that give us the opportunity to use. Let's see. First of all, we have general platform like general formats like Parasolid, which is XT, SAT, SAB, and STEP. In addition, we have IGES And then we have all the main platform like Pro-E, CATIA, SolidWorks, Unigraphics, Inventor, and Solid Edge. So those are all the platform and the general their general format that we can import our geometry, the 3D geometry in our case. So the geometry is this geometry. We have a CAM and a laser and another CAM. This is actually military system. A lot of military application use midas in order to do random vibration, modal vibration, shock, and so on. So after we import the geometry, this is the time we're ready to do simplification in order to have a very high quality mesh. So to go to the simplification, we only have to push the simplify bottom, and then to choose the hole, the fillet, the small edges, the small faces, the silver face, the spike that we would like to remove from the parts in our system. Before, we have to specify which hole we want to remove. For example, all the hole which have the diameter that is 13.4 millimeter and lowest. So the same method for the fillet, small edges, and so on. This is the simplification. Then we are jumping to the material to the material specification. We define the material. For example, aluminum 6061. We have to insert the elasticity module, the Poisson ratio, the mass density, and if we deal with thermal analysis simulation, we have also to insert the conductivity, the specific heat, and the thermal expansion coefficient. So this is the material. Then we have to attribute the material to the property. So this is very simple. Right push on the bottom, and then to attribute between the material and the property. And this is the very simple activity. Then we are ready to do the contact between the part. This is also very simple activity. Add the contact, choose all the geometry part, and then we will have 68 objects that will be connected each to the other. We have several contact types, like welded, like bidirectional sliding graph, general, and breaking weld. So each connection have its own property. We have to choose it, but know all the connection is linear connection. This analysis is linear analysis, and we have to choose linear contact. In the nonlinear analysis, we have the opportunity to choose also non-linear connection. After we specify the connection between all the system parts, we are ready to do the meshing. And in order to do the meshing, we have to right-click on each part or several parts to choose the meshing, to choose the general mesh, and then to choose, the recommendation is to choose hybrid mesh. And the hybrid mesh is a mix of tetrahedron, hexahedron, and the pyramid, for example. We have to specify the size of the element and to attribute to the element the property that the element made from. So after we do that for all the part in the system, we have the meshing. So when we have the meshing for the external part as well for the internal part. So if we want to see the internal part, we have the opportunity to hide the external part. Then we will see all of the meshing internal part. So after we do this activity, the time is to define the boundary condition. In order to define the boundary condition, we jump to the horizontal menu, load boundary condition. So we choose the constraint, and we choose the face that have the connection from the base of our system to the external world. Then we will have all the boundary condition of the system. So if we want to see that, so only to push all the geometrical part. So we define all the connection which are the boundary condition of our system to the external world. Then we are ready to define the PSD curve, which is frequency dependent. Let's see the frequency curve. The frequency curve definition location is here. So here it's the PSD curve. This column is for the frequency. This column is for the PSD value. So this is the PSD curve in a unit of hertz for the horizontal axis and in G square per hertz in the vertical axis. And now we are ready to define the analysis case. First of all, we want to analyze modal analysis. We have to analyze the system frequency value in order not to miss any frequency during the random analysis. So right push bottom, and then we see all the connection, all the part that have been meshed already, and all the connection between the part. Then we can define the number of mode that we want. Here we define 10 mode, which is good enough for this system. And we can jump to the definition of the random analysis. So gentlemen, right now we are in the random response analysis editor. So we can prepare it for the analysis. So first of all, we should define the frequency set. And the frequency set is comprised from increment, frequency increment, and number of increment. First, the first frequency is 10 Hertz, and then we specify a frequency increment of 50 Hertz and number of increment 40. So the analysis will be between 10 Hertz to 2000 Hertz. And then we will specify the frequency load, which will along x-axis, and the frequency function that has been specified before by the graph frequency versus PSD load. So we are ready. The only thing that we should specify is the modal damping function, or we can uncheck this modal damping function and specify uniform structural damping coefficient, which is 0.0.5, which can be specified in the load boundary condition. So this is also defined. So we are ready to running. However, we should specify which and how many sigma our analysis will cover, so that what is the acceleration time that it will be covered, that will be covered by the simulation. So this parameter can be easily specified here. We have the possibility to define 1 sigma, 2 sigma, 3 sigma, 4 sigma, while 1 sigma is one deviation, one standard deviation around the average results, which cover acceleration time of 68.3%, or 2 sigma, which cover 95.4 acceleration time, or 3 sigma, which is 3 standard deviation around the average, which cover acceleration time of 99.7% of the acceleration time. We simulate military system. The requirement for military system is plus minus 3 sigma. So this will be our specification. So now we can run the analysis. So we are going to analysis, and then we push bottom the perform bottom, and we should choose the model as well as the random response, and press OK. We perform the running of this case study before in order to save some time. So we have now the opportunity immediately to see the results. So first of all, let's jump to the results, to the model results, in order to see the resonance of our system. Let's remove the cover in order to see internal part of the system. It's very important to run modal analysis in order to learn the system and the rigidity of the system. The frequency show us what is the system rigidity, and it's very easy to define which part will excite during this vibration. So let's try to evaluate the resonance, and the resonance will be shown in the modal analysis. So the modal analysis is here. So now we are ready to see the modal analysis results. So first of all, see the first mode, which is the frequency is 172 Hertz, and the part which is excite is the mounting of the control card of the laser system. The second frequency is about 200 Hertz, and the laser system is excited. The third is not sensitive, and the fourth frequency excite the inverter of the system in the right side of the camera. The fifth frequency excite the digital PCB. We see here that the digital PCB have the biggest deflection, so This is the excitation here in the 5th mode. The 6th mode also excite this board and the mounting bracket which hold it. Those are the six sensitive frequency mode that the system has a resonance in these frequencies. This is the time to jump to the random response analysis along x-axis, and we can show you the translation, which is the displacement, the acceleration, and the von Mises stresses. First of all, the deflection map in millimeter. We can see the deflection in this scale of all the system part very, very clearly. And then we can see the acceleration, the RMS acceleration under 3 sigma. We see that the biggest acceleration is in the control card, and then we see the von Mises stresses. So those are the outcome of the modal and random response analysis. This is the time for Q&A. However, now it is the time for you to go to try to download the Domo Midas NFX new version, which actually a fully version. So you have the opportunity to use it by yourself and try it and to see how it's very, very user-friendly. Okay, everyone, that's all what I have prepared for you regarding to the random analysis by Midas NFX platform. Now we are ready to start with the Q&A session. Please feel free to ask and I will do my best in order to give you the appropriate answer.